Hi, in this video I'm going to show you how to encrypt and decrypt secrets in a Golang application using a cipher called AES-GCM-256. And the reason I've needed it was because I have been dealing with a service that doesn't support OAuth. So there was no way to just grant access to an application using a web-based flow, and I actually needed to store the login and password for a service in the application in order to use it. And my name is Karol Moroz, and you are watching Make Programming Fun Again. So firstly, I'm going to need to give you a disclaimer. I am not a lawyer, and this is not financial advice. But if you think you can learn something from this video, you can watch ahead. So the first thing I'm going to do is I'm going to initialize a new Go project using Go mod init. I'm going to call it github.com/Moroz, which is my GitHub username, /secrets demo. I'm going to initialize a new Git repository, and I'm going to add the files, and I'm going to commit it. Like so. The first thing I'm going to do is, the second thing I'm going to do is I'm going to install golang.org/x/crypto at latest. Oops. How about this? Oh, not crypt, it's crypto, sorry. And then I'm going to also install Argon2ID. Was it called this? No, it was called Argon2. And Argon2 is a key derivation algorithm, is a key derivation function we are going to use to derive the secret key from a secret key base. And throughout this video, I'm going to be setting quite a lot of environment variables. And for this, I'm going to be using a tool called drenv, which you can read about on the internet. And drenv uses files called .envrc to set environment variables in the local directory, and obviously this file is going to contain secrets, so you should not commit it to the Git repository. So the next thing I'm going to do is I'm going to ignore those envrc files using git ignore, like so. And I'm going to touch a local envrc and an envrc sample, and I'm going to trust the envrc we have just created in this directory using drenv allow. And now the first secret we're going to need is going to be a secret key base. So we can create a secret key base, which is basically a long and very random string using a tool called OpenSSL. You most likely have it installed on your operating system if you are using Linux or macOS, and you are using some sort of programming languages such as Python or Ruby or Elixir. And OpenSSL has a CLI that can generate base64 encoded random strings for us. And in this case, I'm just arbitrarily going to use 128 bytes, which should be enough for in terms of randomness. I'm going to remove the new lines so it fits in a single line of text nicely. And I'm going to copy this value to the system terminal. Now this command only works on Linux. If you are using macOS, you can use pbcopy. It does exactly the same thing. And now in .envrc, I'm going to define this secret key base environment variable. I'm just going to paste the text I had in the system clipboard, like so. And now we trust this file. And the next thing we're going to do is we're going to write some code. So I'm going to create a new directory called config, and I'm going to write some code in the config directory, package config, and I'm going to implement a function called must get env. This function takes an argument called string and returns a string. And what this function is going to do, we're going to check the environment variable with the given key. If it is not set, we are going to print an error message and stop the program. And if it does exist, we return the value. So let's say value equals os.getEnv key. If value is an empty string, we call log fatal f, which prints an error message and stops the program, with the error message saying fatal environment variable with this name is not set, and we pass the key. Then we return the value, like so. And now I'm going to write another function called must getEnv base 64, and this is going to do exactly the same, except that it's also going to try to decode the value in a given environment variable as base 64 encoded binary. So I'm going to call this one encoded equals must get env key, and then binary error equals base 64 standard encoding decode string key, not key, encoded. If error is not nil, log fatal f fatal could not decode environment variable with this name from base 64, and we could print the error message key and error, and if everything was correct, we return the binary. So this way we can now define a package level variable called secret key base, and this is going to be must get env base 64, and we're just going to fetch the secret key base and try to decode it as a base 64 encoded binary. And now in main.go, in the root level of this project, I did not write this code, Go LSP wrote it for me, or maybe it was vim.go. And in here we can try and debug the value of the secret key base that was just generated for us by OpenSSL, and we pass config secret key base, like so. Okay, so now if I go run, we are getting this very long hex value, and if I run it again, we are getting the same value, which means that the based on the observations of 2 runs, the output is going to be deterministic. Great. So now that we have a secret key base, we can try to derive a key, and we can do it using a key derivation function. And in this case, I'm going to use the key derivation function called argon2. You can also use pbkdf, which is included, I think, in the standard library, but argon2 is more modern. And yes, I'm just going to make it local. And this is going to take the secret key base, which is a binary. And this is going to take a salt, which is also going to be a binary. And then it's going to take a length, which it has to be a uint32. And it's going to return a binary, like so. And in here we can return argon2 ID key. And this takes the secret key base, the salt, and complexity parameters 1. The first parameter is time, the second one is memory. I'm going to pass 64 megabytes, which means that this function will always use at least 64 megabytes of memory. And then parallelism of 1, because we may be running this on a machine with only one core, in which case we do not want to spin up more cores, more threads than we have when we have CPU cores, like so. And now we're also going to need a salt to derive a secret encryption, to derive a key for secrets encryption. So once again I'm going to generate a salt using OpenSSL, and in this situation I'm not even going to bother decoding the base 64, because it just has to be some value with enough entropy, and it doesn't have to be so long. So I'm just going to generate 12 more bytes of base 64 encoded data. I'm going to remove the trailing new line, and I'm going to copy it to the system clipboard, not base 32. It's base 64. Okay, and in this salt, we can probably even store in the we can commit it in the source code, because it's not so important because it's basically going to be useless without the secret key base. So I'm going to call it secrets encryption salt, and just going to paste it here, and then we can say secrets encryption key equals derive key secret key base secrets encryption salt, and the length is going to be 32, because we are going to be encrypting things using AES-GCM-256, which takes 256 bits, 256 bit long keys, and that equals to 32 bytes of data. Okay, great. So now we can try and print the secrets encryption key, like so. And now we're getting a different, now in this program we are getting a secrets, a hex encoded value, and we can try to count the length of this, the length of the output of this program, and it's 65. And this accounts to 64 hex digits, and a new line, which means that we are getting a 32 byte long encoded hex thing. So far so good. I think this is a good moment to commit. Git add git status. So now we have an envrc sample, and we have a git ignore. What do we have in the envrc sample? Okay, now it's the envrc sample is empty, so we can basically commit the sample is going to contain just an indication that we are going to need a secret key base, and we could probably also add an indication like OpenSSL rand base 64 128, and removing the new lines, like so. Great. So now that we have derived, I'm going to add again and commit. In implement secrets encryption key derivation. Okay, great. So now the next thing we're going to do is we're going to implement the encryption itself. And this I'm going to do in a new file in config package. And in this package, I'm going to first define a type for credentials, because most of the time credentials come in pairs. So this is going to be a struct that contains a login field, which is a string, and when encoded to JSON will be encoded as login, a lowercase login, and then the password, which is also a string, and when encoded to JSON will be encoded as a lowercase password. And then we are going to define two functions. One is going to be called encrypt credentials, and we're going to pass a secret key base, a secret key. We can just call it secret. And the credentials, which is going to be credentials like so. And we're going to get in return a binary and an error. And then the next thing we're going to do is we're going to initialize an AES cipher, and I think it was done like this. AES new cipher with the secret key. If we get an error, we can return a nil and an error and the error. And then we're going to initialize an AEAD. AEAD stands for Authenticated Encryption with Additional Data. And this is a cryptographic construct which combines a streamer block cipher and a message authentication code, which is a lot of buzzwords, but it basically means it's going to encrypt our data, and it's going to ensure that it has not been tampered with, and that it has not been corrupted in transport or anything. And then we can also use some additional data. For example, we can say that this value is only valid in the context of some specific in some specific context. For example, if we're going to encrypt credentials for a specific environment variable, then we can also validate it with the name of this environment variable. Which brings me to that we can also pass additional data like so. I'm going to call it key, and or maybe I'm going to call it variable name. So, and then we can add some documentation later on. So AEAD error equals cipher new GCM, and we pass the block cipher. If error is not nil, return nil and error. And then we need to generate an initialization vector. And in AES, when running in GCM mode, uses an initialization vector, which if I remember correctly is 96 bits long, which is 12 bytes. And this value is necessary so that we can so that every time we encrypt data, it starts the cipher with in a different way. Basically we just need a 12-byte long binary that has to have enough entropy so that it cannot be easily guessed. And also, no, actually, you know what? the initialization vector is not even a secret. We're going to store it together with the ciphertext. We just have to make sure it is never reused. So I'm just going to allocate a byte slice. I'm going to call it nonce, and I'm going to use the make operator, make function, to allocate a new byte slice. And now it's going to have the length of the nonce size, and it is going to need to have the capacity for the length. Okay, it's going to need capacity for the length of the encoded credentials, which we do not know. Which we do not know the capacity yet because we haven't encoded them yet. So I'm just going to pass a placeholder which is called plaintext. We have not defined this variable yet. I'm going to define it in a moment. And then we pass the, we add the overhead, the value of the overhead to it. And this is because the final length of the AEAD encoded text is message is going to equal to the length of the plaintext plus the length of the nonce plus the length of an authentication tag. Anyway, before we can encrypt it, we're going to need a plaintext. So let's see. Plaintext error equals JSON Marshall credentials. If error is not nil, return nil and error. And now we have a nonce buffer, and we can use rand read to read exactly the length of a nonce of random data. Now what this rand.read does, it is called rand.read, but it actually writes data to the nonce. It's called rand.read, but it actually is going to write data to our byte slice, and it's going to write exactly the length of this byte slice, and the length is currently going to be equal to nonce size. So we are going to generate exactly this many bytes of random data. Also, later on we are going to use the same byte slice to store the whole encrypted message. So it's going to contain the nonce first, then it's going to contain the plaintext, and then it's going to end with the authentication tag. And then return AEAD seal. We're passing the nonce because we are writing to the same buffer. We are passing the nonce as the nonce because right now this buffer only contains the nonce. We're passing the plaintext, and we're going to pass the variable name variable as additional data. Oh, it returns. Yeah, okay. We also need to return a null error, and the AEAD seal only returns a binary. Great. So we could try and test this implementation. I'm going to write a new program called Encrypt, and it's going to be just a single-use script that we can discard afterwards. Package main in function main. We're going to need some credentials, right? So I'm going to go ahead and in the envrc file, I'm going to define credentials, and for the purposes of this video, we can just assume that we are building a program for the agricultural sector, and we are maize farmers, so we are going to have to communicate with a platform for maize farmers, which is called Corn Hub. And we are going to store the Corn Hub username, let's just say it's going to be josh@example.com, and we store the corn hub password. No, not this. Password equals hunter2, obviously. So now we need to trust this file. We're going to have to approve this file so that Diren can set it for us, and we can check that in the corn hub username variable we're getting josh@example.com, and in corn hub password we're getting hunter2. So far so good. So now we can read this username using config must-get env corn hub username, and password config must-get env corn hub password, like this. Then we build a credentials struct. I'm going to call it config credentials. Login is username and password is password, like so. And now we can encrypt it. Ciphertext error equals config encrypt credentials. It takes the config secrets encryption key. It's going to take the credentials, and it's we are going to store it in the environment variable called corn hub credentials. So this is the name I'm going to pass as authenticated data. If an error happened, we end the program. Otherwise, we print the ciphertext to the standard output for testing. I'm going to cd into this directory and go run, and we are getting a ciphertext. And if I run it again, we are getting a completely different ciphertext, but it's exactly as long. So the reason this is happening is because we are using a different nonce every time we encrypt this message. We are getting a different ciphertext, and we are getting a different authentication tag. But rest assured that this is going to decode to exactly the same value. And since this works, we can also encode it as base64 std encoding, encode to string, ciphertext, fmt print ln, like so. So now if I run it, we get the same thing, but it's a bit shorter. Yeah, maybe I should make sure this actually works, but yeah, we can check it later. Anyway, looks legit. So I'm going to copy this value to the system clipboard, and I'm going to add it to envrc sample. Like so, and I'm going to add it to envrc. So now we don't need to be storing the corn hub username and corn hub password in plaintext anymore. We only need the corn hub credentials variable, which is useless to malicious actors without the secret key base. And also we're going to need the secret key base, and we're going to need the exact same key derivation solved in order to decrypt these credentials. So it's probably not watertight. It's probably not watertight, but it's probably still better than storing credentials in plain text. So I think this is a good moment to commit. Direct allow, like so. Okay, git add, git status. Okay, git commit. Okay. And now we can also implement decryption. I'm going to do it in the same file, like so. Func decrypt credentials, and I'm going to take this secret key base, which is a binary. We're going to take the ciphertext, and we're going to take the variable name, which is a string, and we're going to return credentials and an error. So just like before, we need to start by initializing a block cipher. And so AES new cipher with a secret. If this returns an error, we return nil and the error. Then we initialize an AED cipher new GCM with a block. If this returns an error, we return nil and error. And then we need to take the nonce. So the nonce equals ciphertext up to the length of the nonce, so AAD nonce size, and the message is ciphertext starting from the nonce size up to the rest of the message. This looks a bit cryptic, but basically it slices the ciphertext in two, and these are going to be exactly complementary. Like the way this syntax is designed, this is going to be exactly right. So this wasn't clear for me at first, but this is going to become your second nature. If your slicing syntax starts with an index, then this index is inclusive, but if it's at the end, it's exclusive. Go figure. Anyway, the binary and error is going to be AEAD open, and we can pass a nil, and we pass the nonce and the message, and the additional data is going to be the variable name. If error is not nil, we return nil and error, and then we can try to decode the credentials. Error equals JSON on Marshall binary to credentials, return credentials and error, like so. And now that we have a function like this, we can also write a helper in the config.go. I'm going to call it func must decode credentials. It's going to take a string, which is going to be the name of an environment variable, and it's going to always return a pointer to a credentials struct. So first we decode the ciphertext, and this is going to be must get env 64 with the key, and then creds error equals decrypt credentials. We pass the secrets encryption key, we pass the ciphertext, and we pass the name of the environment variable. If the error is not nil, we can print an error message and exit, like so. Fatal, could not decrypt credentials. Oh, we can just pass the environment variable name. And we print the error message, like so. And then we return the credentials. Okay. And now in main.go, we can try to abuse it. Actually, we can also abuse it here. Var corn hub credentials equals must decode credentials corn hub credentials. Okay. And now we can try and debug this variable inside of main.go, like so. Undefined config corn hub credentials. Okay, are we sure? Yeah, I just didn't save the file. Okay, so now we can see that the corn hub credentials are basically just base 64 encoded binary. If we try to decode it, we're just getting a bunch of gibberish, unprintable gibberish. So I guess, yeah. So if we try to decode this ciphertext, it's not even printable most of the time. So I guess this shows that we have correctly encrypted these credentials. Obviously, this is not the most convenient way to do it, because you have to write specific programs for every time you encrypt things. But I guess this is convenient enough for one of situations like this. Also, I do not advise you to use, you definitely should not use this method for AWS tokens. There are much better ways to store AWS tokens, and most of the time you don't even have to generate any keys on your own, because AWS can do it for you. And yes, so if you have enjoyed this video, please consider smashing that subscribe button. And if you don't think this warrants a subscription, maybe you could just at least give me a like. And if you disagree with me rolling out my own crypto, please tell me in the comments below, and I will see you in the next video. Bye.